Okay, let's talk about transmission and reflection at a wave interface. So transmission and reflection. One rule is you never take notes in pencil because it's slow and your pencil will break. Well, just telling you. All right, so let's start with this scenario. Let's say we have a heavy spring, okay, and that is attached to a lighter spring. Okay, so they're connected together. So this point where these two waves interact is called an interface. It's the interface between two mediums, okay? And so what we'll do is we'll draw a wave on here, a wave pulse actually. It's easier to understand. And we'll draw a funny shaped pulse just so we can follow along with what's going to be going on here. So I need my... Okay, so we've got kind of like a triangular wave here. And this is the initial condition. This is the input wave traveling to the right. So we'll give it a velocity in that direction. All right? Now, one thing to note is that waves travel faster in the lighter spring. Okay? So one thing to note here is velocity is lower. So the speed of the wave traveling is lower in the heavier medium. Okay, and that might make sense to you because if you know Newton's laws, then you know the first law is the law of inertia, and essentially inertia is mass, right? And if something has more mass, it requires more force, more effort, if you want, to move it. So if the resting condition is here and it has a lot of inertia, it takes more effort to move it. That translates into overall the wave moving slower through this heavier medium, okay? So this wave is traveling along and it's approaching the interface. At any interface, some wave energy is transmitted and some wave energy is reflected. Okay, so what will that do? So let's draw. Let's draw the after situation. So this is after the wave has collided with the medium. I'm trying to keep the same colors, but I forget which colors I used. I think they used this one. Oh, not quite. Okay, so at this interface, some energy goes into the new medium. And what will end up happening here, okay, I'm going to do a little explanation of what's going on. The reflected wave is going to have a lower amplitude. Why? Because some of the energy that was in it transferred into this wave. The height of the wave is an indication of how much energy that wave is carrying. Higher amplitude means higher energy in the wave. Okay? The reflected wave, well, it's going to be on the same side. The reason why it's going to be on the same side is because when a heavy spring collides with a light spring, it behaves more like a free end reflection. Okay? So we'll get this coming back with a slightly lower amplitude. That's meant to be a slightly lower amplitude. Okay? And we'll get this transmitting through on the same side that it went in at. I'm going to add, let's see here. Oh, not the right weight. I'm trying to do a whole bunch of stuff at once here. Okay? So this is your after condition. Now the velocity here in the heavy spring is the same as it was before because this medium hasn't changed. But the velocity in the new, okay, the velocity in the new spring is going to be higher, right? Now, I'm going to get a little technical here for a second. This is a single wave pulse, right? We're just talking about a single wave pulse, all right? But if we weren't, if we were talking about a wave train and we were talking about frequency stays constant. And that's going to give some properties that we can predict to this new wave. So whatever frequency we have here is equivalent to whatever frequency we have here. but we already mentioned that velocity changed. So if we have two waves of the same frequency, but different velocities, what else must be different about them? So that's the question, okay? So, and actually, let's throw in numbers just for fun. Let's say this. The frequency of the heavy wave, or input wave, is 10 hertz. Therefore, frequency of transmitted wave is also 10 hertz. And why this is so should be sensible, right? I'm jiggling the particles in this, right, at the same frequency, and then, you know, that means that the particles at the end of the heavy medium are jiggling at some frequency, and that is affecting the particles in the new medium, and they will jiggle at the same frequency. So frequency of waves upon transmission never changes. That's going to be very important because it's going to allow us to predict the properties of the wavelength over here. Okay? So remember we said this before, right? Velocity is equal to frequency times lambda. That's the wave equation. We've had that before. Or, if we want to rearrange this, frequencies are equal to v over lambda. Okay? So in this case, we've said frequency here equals 10 hertz. We've said frequency here equals 10 hertz. Okay? So what if the wavelength over here, let's say the wavelength over here is sorry, let's make the wavelength over here, let's make it 2 meters. So lambda is 2 meters. So the frequency is 10 hertz, and the wavelength is 2 meters, and we said frequency equals velocity over lambda. What does the velocity on this side have to be? Right? Now we said it's going to slow down over on this side, but we're going to keep the same frequency, right? It's going to slow down over on this side, but we're going to keep the same frequency. So let's say we have the velocity. Or sorry, double the velocity, my bad. It doesn't slow down, it speeds up. What am I saying? It speeds up. So let's say that the speed over here is 40 meters per second because it's sped up in the new medium, right? It's sped up as it went to the lighter medium. What does that say then that the wavelength would have had to have done as well? It must have also doubled, right? It must have gone up to 4 meters, okay, to keep that frequency at 10 hertz. So essentially, the takeaway from that is that when the wave speeds up, in order to keep the same frequency, it must have a longer wavelength, right? The wave is coming faster. So in order to keep the frequency the same, it has to have a longer wavelength, all right? So in the new medium, this will actually have a longer wavelength than it had in the old medium. Probably look more like that, right? So it has a longer wavelength. So that's a key takeaway from this, and I'll write that down in notes. So, upon transmission, if the transmitted wave is faster, it must also have an increased wavelength. Okay? So I'm going to write a little formula. I'm going to write a little formula that we can take away from this. So we know that frequency is V1 over lambda 1. So frequency 1, the frequency in the original medium, is V1 over lambda 1. And then frequency in the second medium is the new velocity over the new wavelength. And we also stated that frequency can't change. So frequency 1 equals frequency 2. So if that's true, then this must also be true. V1 over lambda 1, the ratio of those two things, is the same as the ratio of V2 lambda 2. We'll pause there. So the best way to think about it is just like this, right? If we're slowing down, so we have a train, right? We have a train here. The train's moving along, and then the train enters like a new area of tracks where it's got to go slower. Now, in real life, you can't change the size of a boxcar, but if you get onto these new tracks, right? So let's say now we're a wave going from a fast medium to a slow medium, right? But we need to keep the same frequency, right? This rate of these boxcars going by has to be the same. Well, if we slow down the overall speed of the train to keep the frequency of boxcars the same, we got to have like shorter shorter boxcars, right? Shorten up the boxcars, and you can have the same frequency even if you're traveling slower, right? So the new train has shorter boxcars. So this is going the opposite way. So let's just doodle that in. Actually, this is a better way. Instead of trying to switch to the fat rope every time, let's just like draw a fatter line. There we go. Okay, so if we send in a wave now, that looks like this. Okay, there's going to be some portion of it that is reflected at the interface and some portion that goes into the new one. So the first thing to note is if the wave slows down in the heavier medium, it's going to have a shorter wavelength, right? So the wavelength will be shorter here. So shorter wavelength. Shorter wavelength. And then the reflected wave, oh, you know what? What did I do? I should draw this in a new picture, shouldn't I? Let's get rid of that. It will have a shorter wavelength, but it's going to be confusing if you look at it in notes if I don't redraw the picture. So this is going to be after. So we'll draw this first. The transmitted wave is always on the same side, but its properties might change in terms of wavelength. Well, they will change. So we have a shorter wavelength, but the amplitude's on the same side. But now we've reflected off a heavier medium. Okay, so going from light to heavy, that acts more like a fixed end. So it acts more like a fixed end. So more like a fixed end. So what do you think is going to happen to the side of the amplitude? It's going to invert, isn't it? That's exactly what happens. So the reflected wave heading back the other way gets inverted when you go from light to heavy. The reason being is because it's behaving more like a reflection from a fixed end. Okay? So we've got shorter wavelength, right? Because we've got lower velocity. And we figured out that the ratio of the two things always stays the same. You know? So this is a 1-to-1 ratio. If this is going slower, then this has to go slower in proportion. And the wavelength has to be shorter in proportion to keep the same value. Okay? And that's kind of like the deal with reflection and transmission. Later on, we'll talk about what happens when, say, something like light strikes onto the surface of water, and some of the light actually can travel into the water, and some of the light reflects off the water. And I'm sure you've noticed this in everyday life, but later we'll be applying these sort of simple wave ideas to more complicated scenarios like water. So that's why we spend some time learning this stuff. Are there any questions? More like a fixed end, okay? So I can actually just, you know what, I'll just write that in a note just to wrap it up, okay? So reflection off a heavier spring causes an inversion of the reflected wave. Okay, i.e., behaves more like fixed end reflection. Okay? The wavelength in the heavier medium after transmission will be shorter. Tomorrow